Hello and welcome. I am Anubandh Ori, and today I'll be taking you through the applications of pumped hydro storage, or also referred as PHS, as the most mature and widely deployed energy storage technology globally. PHS plays a crucial role in supporting renewable energy integration, stabilizing grids, and more. Next, I would like to talk about the working of PHS. Pumped hydro storage operates by moving water between two reservoirs at different elevations. During the time of excess electricity, water is pumped uh, through from the lower reservoir to the higher reservoir. When the demand rises, it's released to flow downhill through the turbines, generating electricity. This conversion of gravitational potential energy into electricity is both simple and effective. For the turbine part, reversible turbine generator assemblies are most commonly used. They are also referred as Francis turbines. They allow water to be pumped both uphill and released for generation. This reversibility is central to the uh, functionality of the pump storage. Over here in this diagram also we can see that this is the generator, the turbine part, and this is the lower reservoir. So when we have excess amount of electricity, it will be used to pump the water from the lower reservoir uh, to the upper reservoir, and when there is demand for more electricity, the reverse action takes place. Next, we'll be talking about the history of PHS. PHS technology is not a new concept. It has a long history since 1890s when the world's first PHS appeared in the Alpine regions of Europe with a separate pump motor and a separate generator turbine. The concept of a reversible pump turbine machine was then introduced and implemented in the year of 1950, which was widely appreciated and adopted in the coming years. But due to development of nuclear energy in the early 1960s, the development of PHS was significantly slowed. It was after some time when there was a realization of the environmental concerns caused by nuclear radiation and pollutions caused by fossil fuels. PHS then got a support for sustainable development. Next, we will discuss about the global install capacities of PHS. According to the IHE report published in the year 2018, the global hydropower install capacity is around 1200 to 1300 gigawatts. In addition, IHE reports that hydropower generated about 4,000 ton watt hour of clean energy in the year 2017 alone. These figures are all globally. If this electricity was replaced by fossil fuel energy, approximately 4 billion tons of greenhouse gases would have been emitted, and the global emissions would have been higher than 10% than they are at present. So, so if we look at the slide over here, we can see that this graph shows the various installed capacities of various energy storage devices globally. One thing we can see that PHS, that is pumped hydro storage, it is about 99% of the total capacity. So the fastest growing country with respect to the PHS is China with an overall capacity of 9.12 gigawatt, followed by Brazil and India. PHS again has the biggest share of 99%, and it has a efficiency of energy storage capacity efficiency of between 70 to 85%. Now, next we can discuss about the categorization. Although there is no formal categorization of PHS, but due to the large variation in the sizes that is presented in the literature, it can be classified into four categories, that is large, small, micro, and pico. So large PHS storage are the one that generate electricity that is greater than 10 megawatts. Small will be somewhere around 100 to 10 100 kilowatt to 10 megawatts, and micro will be between 5 kilowatt to 100 kilowatt, and pico will be the size below 5 kilowatt. So irrespective of the PHS size, the efficiency of the storage varies between 75% and 85%, while some studies claim it to be up to 87%. Moving on to the application of pumped hydro storage. So first we have is the integration with the renewable energy. So as we scale up solar and wind capacity, managing the continuous fluctuations becomes a challenge. Solar generation, as we know, peaks during the midday, while often the demand peaks in the evening. Wind is even less predictable. Pumped hydro bridges, pump PHS in this case, bridges the gap by absorbing the excess generated electricity when it's not needed and supplying it back to the grid during the demand spike. This enables a higher penetration of renewables into the grid without compromising the stability. Next would be the grid services like frequency and voltage regulation. The grids need to maintain a constant frequency, usually between 50 to 60 hertz, to operate safely. Any imbalance between the supply and demand can cause the frequency deviations. PHS can respond fairly quickly to provide or absorb power, stabilizing both the voltage and frequency. It acts like a shock absorber for the grid, preventing blackouts and helping integrate more renewable sources smoothly. The third application will be time of use electricity pricing and energy arbitrage. So one of the first things we discussed was like using it for renewable energy and storing the power during the peak and delivering it during the highest demand. The third option can be used with the regular fossil fuel type of energy generations. Say we are using natural gas plants and diesel power plants. So electricity prices fluctuate throughout the day based on the demand. PHS takes advantage of this by pumping water to the upper reservoir when the electricity is cheap, usually during off-peak hours, and releasing it to generate power during the expensive peak hours. This allows utilities to profit through energy balancing while supporting the grid efficiency at the same time. The fourth application will be the daily and seasonal energy balancing. So, unlike batteries, which are best suited for short-term fluctuations, pumped hydro can handle both cycles and seasonal shifts. In regions where the snow melts or monsoon-fed rivers, water can be stored during wet months and utilized during the dry periods, ensuring a reliable power supply all year around. So before we move on to the exergy analysis of one of the PHS systems, I would just like to show this diagram which shows the variation in solar energy available throughout the day. We can see that in the region 1 to 2, it is bare minimum because of the sunrise. And as we approach the midday, the amount of solar radiance that is available is at the highest. So energy at this point, if we are able to produce more electricity than we need, the excess can be stored in a pumped hydro storage. And as we can see, as we have a cloudy day like this, we can then use the excess water stored to generate electricity and meet the demand. We need to generate electricity to meet the deficit that is there in the orange part. And then again, once the clouds disappear, we again have and increase in the sunlight, and we can again switch back to pumping the water back for the use at night. Now let us have a closer look at the exergy analysis uh, of the given system. We begin on the left of the input power from the grid over here. We can see that it's around 100,000 kilowatts. This shows the exergy entering the system. So exergy in simple terms is the maximum useful work that a system can deliver till it comes to the equilibrium position with its surroundings. The idea of exergy is that as long as I have a pressure difference with the surrounding, I can put a turbine and extract work. And as long as I have a temperature difference with the surrounding, I can always put a heat pump and extract work from there. Unlike energy, which is always conserved, exergy is destroyed in every real process due to inefficiencies and irreversibilities. Uh, Processes in real life are not reversible. That's why exergy analysis is such a powerful tool. It helps us locate and quantify where and how these losses are taking place. In this case, as the electricity powers the pump, this is the pump, about 99.8% of the electrical exergy is delivered over here. However, if we move further onto the right, we can see there is a fall in the exergy available. This is due to the mechanical and hydraulic inefficiencies, which reduce it to 93.14%, which is nearly a 7% decrease in the available work. This is just during the pumping process. Once the water is pumped to the upper reservoir, there is a very, very small loss of 0.2% to evaporation, leakage, or thermal dissipation. Now, when we come to generating the electricity part, we flow the water from the reservoir to the turbine, and during discharge, we again have some exergy loss. In this case, it is around 15%. And this could be due to the hydraulic friction, the bends in the penstock, turbine efficiencies, the generator losses. Ultimately, we deliver around something around 78,346 kilowatt over here, and which means that the round trip exergy efficiency for the entire cycle comes out to be around 78%. This diagram over here helps us to identify where the most exergy losses are taking place, which is actually in the pump and the turbine, and not in the storage, as most people will think of, like, okay, water is getting evaporated or there is leakage. No, it is due to the friction and inefficiencies of the turbine and pump, where we are losing most of the useful work. So while energy efficiencies tell us about how much energy is conserved, exergy efficiency tells us how much of that energy remains useful, which is far more relevant for engineering decision and design making. Now, to conclude, pumped hydro storage is more than just a legacy technology. It's the backbone of the global energy storage, enabling everything from solar integration to grid reliability and time shifting of power. Its proven performance, long life, and ability to scale makes it essential for a renewable driven future. And with innovations like micro PHS and closed loop systems, it is becoming more viable in locations that were never planned before. Through exergy analysis, we go beyond surface level energy metrics and truly understand where improvements can be made, making the system smarter, cleaner, and more efficient. Thank you.